Peter Roos is a CEO of Novatron Fusion Group, which is the leading fusion energy initiative in the Nordics. He has a long entrepreneurial background within technology companies and is a former developer. His work has been related to organizational and business development for high-tech companies, with the purpose of making their development organization more efficient. Henka Taubiti is CEO of ST1 Biocraft. He has extensive experience in managing various energy sector value chains and energy transition. Previously, he was the CEO of North European Oil Trade. In this session, they will explore technical challenges, promising breakthroughs, and the roadmap from experimental devices to commercially viable zero-carbon fusion energy. We will first hear the presentation of Peter Roos, and then go into a conversation, into a Q&A session with both of the speakers.
The question that I have is for you, the audience. And how many of you have heard about fusion and know thematically what it is? All right, most of you are. That's great. That is not necessarily the case, actually. And I'm glad, because fusion do have a potential impact on society at somewhat comparable to introducing fire to humanity or the wheel. When it is well implemented in society, it will be a total game changer for how we live our lives, I dare say. And I am not the only one saying that. So we are, around the world, about 50 companies running a roadmap where we try to make the technology commercial viable. We have different approaches because making fusion work at scale is very, very difficult. Society, researchers, humanity, industry has been working with that for nearly 100 years. So there are different ways of doing it, and we have found a way, based upon an innovation, which I will explain briefly here soon, that makes our way to implementing fusion in society and industry a more capital-efficient way to do it. Meaning, it's cheaper, faster, and better in any way, both in development, to develop the technology, as well as actually building the power plants that are hosting fusion energy, reactors, and also how to maintain and operate them. And by the end of the day, why is that important? Well, because we, the consumers of energy, we are not willing to pay a much higher price of energy than we are doing today. Rather, we would love to have a combination of a sustainable energy source that is even cheaper than it is today, right? That's at least a wishful thinking. And what the prognosis says about this type of solution that we are about to provide is that it actually is outcompeting other energy alternatives. So that's good news, I dare say. So, right, fusion. Why should we have fusion at all? I mean, there are so many other ways to actually add a sustainable energy source into our grid systems and into industries. I mean, we have solar, we have wind, we have hydro, we have so many new geothermal ideas as well. Well, the interesting thing is that if you kind of cherry pick the very best of all the different things that these alternative energy, sustainable energy sources have, fusion have them as well. But it doesn't have the bad aspects of the fossil industry or the traditional nuclear industry with long-term waste, radioactive waste. So it's a kind of a wishful thinking, or, as it turns out, the holy grail of energy. And this has been known since nearly 100 years, so that has become quite clear. We should really strive for it. But obviously, we still don't see any fusion reactors producing energy to the grid, so it has been very, very hard to do it. So is it in vain? Is it hopeless? Is it just a futile idea that will take another 30 years and 30 years after that before we actually see it? No, that is not the case. We have had extreme progress in development of fusion technologies, as well as breakthroughs in research that has actually put us to a place where we now are, within the next decade, we will see fusion power at scale and introduced to the grid. So we need to relate to that, understand what it means for us, the potential benefits of that, but also see how we can act in a responsible way to make sure that this type of solutions is available and affordable for the whole entire world, not only the Western world. At least that is one of my own perspectives on how to make this world a better place. So very, very briefly, this is the only physics side. I'll expect from one slide that will present a little bit about magnetic fields, but this is what is fundamentally is what fusion is about. You know, traditional nuclear, you'd use heavy atoms like uranium. You split it in two and you release large amounts of energy. But actually, you can also do the opposite, because that is what is happening in the core of the sun. You fuse light atoms instead, in this case, hydrogen, isotope versions of hydrogen. They are called deuterium and tritium, but they are actual hydrogen. When you fuse them under high pressure and at high temperature, you get helium together with a high energy neutron. And that energy in that neutron, you can harvest it in walls that will be heated up. That heat, you can heat exchange and run gas turbines that will generate electricity. Or you could use the heat itself for industrial purposes, for instance, or heating up our homes. So that is the fundamental core. It's very easy at that level. The difficult part is, how do you do that at scale and continuously? Because fusion, we managed to do fusion already in the 1930s. So nearly for 100 years, we know how to do fusion. But it doesn't make sense if we can do it in a large scale and continuously. So what are the trends now that are driving fusion to actually happen now? The implementation, the solutions, the last pieces that we're lacking. Well, there are a lot of mega trends that are actually supporting us and giving extra fuel to accelerate the development of this and the implementation, of course. We have technology things that have happened that really makes it possible for us to accelerate very advanced development. Because go back in time like 20 years, if you had an idea of how you could develop some kind of piece of technology that is necessary for actually making a whole reactor to work, you needed to actually build the stuff, test it and run it and learn from it, which is a very slow cycle of learning, and it's quite expensive as well. Now, as computer power has increased significantly, and we have AI, we can actually simulate the model. We can model what is happening inside the reactors. We can model the actual technology itself. Actually, our company is building like 100 different versions of fusion reactors every day, which would have been a total, absolutely impossible thing to think about like just 10 years ago. So that is something that is kind of making the capabilities of developing this type of technology now in our hands. At the same time, we also have geopolitics. I don't need to talk with you about geopolitics, but for obvious reasons, we have a climate situation, we have an energy situation. There are so many applications that need large amount of energy. We have data centers, but also we need to produce drinkable water, which requires a lot of energy, for instance. We need carbon capture solutions, which requires large amounts of energy. There are so many drivers. The need has never been bigger than it is right now. That also adds a political will as well as funds, meanings that we have a lot of more money that is pouring into this, both research, but more importantly, the industry that is developing this and is about to implement this. So there are things that is making it potent and capable of actually accelerating this. There are other things that is happening right now around the world that makes that we are not having a linear development of the technology, rather a very accelerating type of development. So I was mentioning that the development of fusion, just to begin with, it was first in the early 1920s they understood what fusion is, and that is what is happening inside the sun and all stars. that is emitting the energy that we are now actually harvesting as soon as we go outside and see the sun and enjoy it. 1930-something, the first time for actually creating fusion on Earth, a mini version of the sun, you could say. Soon there were different type of concepts to make these kind of a machine that could be actually doing this for scale and continuously. The first versions, we had something that was called a mirror machine, where you heat up the hydrogen to a plasma, and that is the topic of the theme of this presentation, right? Because when you heat up a gas to a very high temperature, the electrons will loosen up and be they are totally free from the core, the nuclei of the atoms. So at that point, to making that happen, you have the plasma heated up at extreme temperatures, because we can't simulate the pressure that we have inside the core of the sun, right? The sun is massive, it's very heavy. So the gravity compresses the hydrogen to something that makes it very, very hot, but also very dense to the extent that we have a temperature of 15 million degrees inside the core of the sun. Here, to make something that can work in a similar way on Earth, we need to heat the hydrogen up to 150 degrees Celsius, which is it's very hard to grasp, right? There are no materials that can contain something that is at that type of temperature, obviously. So how do you solve it? Well, you have the hydrogen inside a vacuum vessel, you heat it up to these extreme temperatures, and how crazy it may sound, 150 million degrees isn't that hard actually. We have reached temperatures to 600-700 million degrees, so we know how to heat the plasma up to those extreme temperatures. Then we use magnetic fields to control the plasma, to make sure that the plasma is in the center of this so-called big vacuum vessel. And there you are adding more temperature by radio waves and different other type of technologies, but you must make sure that they don't hit the walls. Why? Will it explode or will the walls melt down? No, actually not. What will happen is actually the opposite. The process will stop. It will totally terminate the process of it will turn back to become a gas instead of a plasma. So it's not a problem for materials or the self. It's that the walls will cool down the process to stop it. All right, so if that is the case, so how can we sustain this plasma a long time, having these in a stable way confined? We can have mirror machines where we have magnets, where you have this plasma bouncing back and forth, the nuclei, they collide, and they will create helium, and you have this high energy neutron. There are other ways to do that as well. We have rotating plasma in so-called tokamaks, where toroidal vacuum vessels, like a donut, you know. There are stellarators. There are also ways of actually doing this with lasers. There are different concepts on doing these, and all of these have been progressing over the times, solving problem after problem, developing new technology, new materials and things that is needed to actually make these possible to a commercial scale. Novatron, the concept that we are hosting, and also is why our company name is Novatron Fusion Group, has in 2024 commissioned our first machine, the first machine of 4. I will show you a roadmap briefly, where we actually for 1 year now has been running a machine that has a proof that it can contain this plasma in a stable way. So how can we see that we are close to a verge where we have fusion in our societies and industry? Well, one way of interpreting the progress is talk about the Q value, which is a kind of an efficiency value, where the amount of energy that you put in compared to the energy that you get out of the process is the quota, that is the Q. And obviously, you would like to have more energy out of the process than you put into it. So if you go back to like 1980, you would have to put in 10,000 times as much energy into the process than you would actually get out of the process. Not a very good machine for producing energy, right? But that was the stage where you were at in the early 1980s. So what was the problem then? Well, the problem was to have a stable confinement of plasma. They have progressed the technology over the time, and actually now we are at a stage where we get just as much energy out of the process as we put into it. So in like 45 years, we have become 10,000 times better at running a fusion device than we were like just in the 1980s. And how much better do we need to be? Well, actually, to reach a stage where we are commercially viable, you need to have a Q value of 30 or more. So, to put that into perspective, we have in 45 years become 10,000 times better. We need to become 30 times better. If you put that into mind, you see that, okay, we are close to the finish line right now. We are not that far off. And that is why private capital is now entering the stage. Industry is actually setting up plans of how do we put this into our energy system? How do we build value chains? How do we make money of this? How do we scale this? How do we build supply chains, etc., etc.? That is happening right now. Most of us don't know that. All right, so what are our add-on to this field, all this research, all this development that has been going on for nearly 100 years? Well, there's this guy who happens to be a Swedish well-known inventor in the Nordics. He's number one when it comes to, for industrial applications, build technology that by using strong magnetic fields, control plasma for industrial applications that already exist. Like for back in the days, you who are old enough, CD discs, the metallic shield, that type of inventions that put an exact amount of layer that was actually metallizing the CDs. That is actually plasma. It's an industry where you put plasma by controlling magnetic field and applying it to the surface. So he's the inventor of that type of technology, as well as he has a lot of inventions and patents also in the solar cell industry as well. So he was kind of thinking about the stability issue, because that is the remaining big challenge still in the fusion industry. How can we make sure that we have this fusion process, we know how to do that, we know how to heat it, we know how to feed the hydrogen into the vessel, all right? But it terminates because at some time it will just hit the walls anyways because it's unstable, and it will stop the process. So we're thinking, okay, so it's about how you shape the magnetic field to make sure that the plasma doesn't hit the walls, right? It's a no-brainer in that sense. But it has intrigued scientists and engineers for nearly 100 years. So he came to think of how to do it. He presented that to the leading researchers in the Scandinavian. They couldn't see any flaws in the solution, but they were kind of, right, but is this really, we are not the experts in this type of concept. You should really talk with the expert, the number one expert, which happens to be a professor at Berkeley in the US. And I will just very soon get back to what he said. Because the invention that John said, the best way to describe it is this picture. What you're doing now with the other concepts is that, see the magnetic fields that is like a bowl that is put upside down. And you try to balance the plasma. In this place, we just put a ball on top of it. You want it to not hit the walls, and therefore you need to do some really smart tricks to balance that on top of that magnetic upside down bowl. That's the big trick, and that is what most of the concepts are working with right now, to try to solve that for a stability reason. And that is obviously unstable. If you don't do anything, the ball will fall down and hit the wall and terminate the process. Obviously, you would like to have the opposite. You would like to have the ball in the right direction, right? Because if that is a really angry cat in the cage and wobbling around there, it will still end up in the bottom of that of that bowl. So that is what we're doing here. Creating a magnetic field that is concave in every direction from the plasma perspective. Making sure that we don't need any smart tricks to keep the ball on top of the magnetic hill or upside down bowl, but implement a static magnetic field that is that bowl that will self-stabilize the plasma. Still, this is no no-brainer. This has been the obvious way to go since the 1950s. But the engineers and the scientists couldn't figure out a way how can we configure magnets to create a magnetic field with this type of properties. And that's Mr. Jadeber's invention. And when he presented that to this professor at Berkeley, Mr. Ken Fowler, he wrote back a letter and stating, well, concluding into one big interesting sentence, the Novatron concept appears to be the missing link. Actually, and he's now a Nestor for us and is supporting us very much well from Berkeley. He's pretty old though, but he's still sharp as a knife in his mind. And he said that in the 1980s, when we were kind of investigating this path that you have pushed, if we had had the Novatron concept there at that time, the world would be populated right now with fusion reactors supplying us with endless of energy. So he is convinced that this is actually the way to go. That was, of course, inspiring John to start the company. And now we are located in Stockholm, in Sweden. And we are now a little bit more than 70 employees, growing rapidly, developing the technology. And as I mentioned earlier, we have actually built the first machine that proves that we have this type of magnetic field properties that have a stable confinement of plasma. So that is important, but also very important. I mean, we are a company pursuing a technology that still will take time to develop and put it onto the grid, and put it into industry and society, where there is a long time before we actually get revenues from selling things. So, and it's costly to develop this technology. How do we prevail? How can we sustain as a company? Well, of course, we are very dependent on our partners. And they are in the Nordics, well renowned, they are very important, they have a long-term perspective on things. But most important for us, the game changer from this perspective was when ST1 entered the stage. And who is ST1? Well, ST1 is an energy company, one of the largest in the Nordics. And from being a fossil industry representative, like any gas company like Shell or BP, they are now running an agenda, driving the transition to an emission-free energy system. So when they found us, they said, let's do this. Let's make sure that we can put energy produced by fusion reactions to the grid. And that's a perfect marriage, according to me at least, because then we have the existing industry with the need, who are already into the energy system, and we have an invention, we have a technology that needs to be released into this society. So, right, we have built a machine, it is up running, there are a lot of visitors from all over the world coming in to see it. We have, by that, the solution for a stable confinement. The second machine that we're about to build, we will start the construction this year, is the one that will create a high efficiency yield of the process. Because our concept is based upon those mirror machines that I was mentioning in an earlier picture before, where there were some issues with end losses, where plasma was leaking through those magnets. But we have inventions to that as well, based upon the same concept. So that is what we're going to do with the Novatron 2. So that will be built, started this year, and in 2028 we will have it commissioned to start doing experiments on it. That is a very important milestone for us, and I would dare say for humanity, because it's a proof of concept of it, that it actually is sustainable, it can work continuously, it's stable, it can produce energy at scale continuously without stopping, cheap. Then it's up to industrialization and scale up and put it out into the grid. So that is where we are right now, okay? So it looks very, very promising. Of course, there are technical challenges, but I dare say that the biggest challenges for us right now is to make sure that politics really put this high up in the agenda, that we really need to put this into the energy mix, prioritize it, which is actually also happening. A lot of industry countries are now setting up strategies and agendas, fusion strategies as well, but we need to accelerate this. Also, we need to put more effort, we need to educate more people, and of course, it's costly, so we need more money, obviously. Actually, that was my last picture. Like I mentioned earlier, it was a pivotal moment for us when ST1 became our largest external owner in the company. And not only because it's a good financial support, but also that you are, like I said earlier, an important part already in the energy system. For the audience, why fusion? Why not something else that seems easier or yeah?
To bring a little bit of context, ST1, Peter was very polite and said that we are one of the biggest energy companies in the Nordics. If you think that there's not that many, then yes, but still as an energy company, we are fairly small, and maybe even because of that, the question is even more relevant that why fusion, why we are today an energy company, energy transition company, operating in Finland, Sweden, Norway, mainly in transportation, road transportation, marine, aviation. We have a refinery, we have a biorefinery, we produce renewable diesel, sustainable aviation fuel. We have a sizable biogas business. Actually, the ST1 Biocraft is the biogas part of our company. I'm chairman for that company, but for ST1 I'm the CEO, and then so we've been kind of and we've been investing quite a lot into the EV space in the Nordics. We used to be one of the biggest wind producers in Finland. When we started to have too much of wind, we divested that business because we saw that it's starting to be quite difficult as a business. So we've been pretty much in all of the kind of areas where energy transition is going forward in the Nordics. And while we've been doing it, we've been studying the energy transition as a whole, and fairly early on understood that we just don't have those technologies available in a scalable form that we could actually, on a global scale, get to the end goal with all of this. And with the owner of the company established a vision for the company already 20 years ago, which is to be the leading producer and seller of CO2-aware energy. And that was a time when we were really, really small. But again, the mindset was that we want to take the energy transition forward. But while we've been investing green hydrogen derivatives and all sorts of things, we've been looking into really deep geothermal projects, etc. We've been very, very convinced that we just don't have those technologies. And then ever since, we've been putting quite a lot proportionally money into R&D efforts to actually get to a state where we could contribute to something that actually would then be globally scalable as a renewable energy source. We were looking at fusion a few years back. I think 3-4 years ago we made a study trip. We went to MIT in Boston and went to visit the Commonwealth Fusion System, which is a big fusion company, if not the biggest private one today. And we realized that a lot is happening in the fusion space. Our initial thinking was that we need to get the Nordics ready for this. We need to raise the awareness in the Nordics that actually we are starting to have companies that will actually be starting delivering power to the grid soon. And we didn't see anything happening in the Nordics. And we tried to figure out a way how to start getting the Nordics ready for all of this. And we're thinking of ways of coming up with some sort of a community. But while we were looking into that, we realized that there is already a company and a small community in Stockholm. And that's the way we found Novatron. And it was very easy when we looked into the technology I'm a commercial person, so I don't understand any of it, but a lot more clever people studied it for us, and we became quite convinced that there could be something here. The point is not that is there something here or is there not. The point is that we need to do something. We have the responsibility of investing into these kind of R&D projects, which are extremely credible. If you put 70 plus really smart people into the same place and give them the money to research, they will come up with really clever stuff. And we've now been a year with Novatron, and it's been an extremely exciting year. A lot is happening in the fusion space. A lot has happened with Novatron. Your company is going exactly by the roadmap that was presented to us a year and a half ago. We've become firm believers that this is coming a lot sooner than later, and we just need to now raise the awareness, make sure that power companies all over are introducing fusion into their strategies. That way we get a lot more money into the industry. We need to get the regulators ready to come up with kind of a framework that allows and makes it easier for this kind of an industry to come about. And we've been concentrating on the Nordics, but I think, at least I feel that my duty is to go all over where I can and talk about the case and raise awareness and support in the best way we can. So,
Thank you.
A little bit of a long answer to a very short question.
Important.